Okay, this is the beginning of Unit 2. In this unit, we are talking about free fall. This unit builds upon our knowledge from Unit 1, especially regarding acceleration. So if you need to, go back to Unit 1 and review acceleration. We will be using one of nature's most accessible examples of uniform acceleration: free fall. Free fall is defined to be motion occurring, quote, under the influence of gravity. The motion can be straight up or straight down. Later in Unit 4, we will study projectile motion, which, for example, is the flight of a baseball, where a horizontal motion is also present. A student of Plato named Aristotle, ancient Greece, wrote the first physics unit on free fall. He said, number 1, objects seek their natural position. So, what are the 4 elements of the ancient world? There was air, fire, earth, and water. Four elements of the ancient world. So objects seek their natural position. So these 4 elements would have a certain natural order. At the base of that order would be Earth. Just above the Earth, we would find water. Then we would find air. And at the top, fire. So objects seek their natural position. In this order, they would rearrange themselves to be in this orderly state. The second thing he said is that rate of fall is proportional to weight divided by resistance. Proportional, we're talking about varies directly. So Aristotle says that rate is proportional to, so we're going to put a K for proportionality constant, directly proportional to the weight and divided by the resistance. So the first physics book stated that an 8-pound ball will fall at twice the rate of a 4-pound ball. When you're in class, I'll give you a demonstration and we can figure out if this is true or not. Centuries later, along came Galilei. He came along and questioned Aristotle's claims. So Galileo claims that, number 1, all objects fall at the same rate if resistance can be ignored. And number 2, significantly, free fall is uniform acceleration. Uniform acceleration was a concept that we started in Unit 1. It is very useful for us in Unit 2. And so you might go back to Unit 1 and review, what exactly do I mean by uniform acceleration? To support argument number 1, Galileo did 2 things. He argued with Aristotle and created a paradox. A paradox is a statement that seems to be true in two different and contradictory ways. If an 8-pound ball falls at twice the rate of a 4-pound ball, what would happen if we glued them together? So scenario A, here's an 8-pound ball, here's a 4-pound ball. First possibility is they will fall at some average rate. There's one possibility. Maybe it'll fall like a 6-pound ball. The other possibility is that they will fall like a 12-pound ball. Meaning faster yet. He took his physics class on a field trip to the Tower of Pisa and dropped some objects of different weights. The lab report written by his students said that the objects landed within 2 finger breadths of each other. For an object that's approximately 50 or 60 meters tall, 2 finger breadths, being maybe an inch or 2, is maybe subject to error, negligible. From a newspaper article, apparently Galileo either didn't do the experiment or he fudged the results. He had claimed that 2 objects of different weights landed at basically the same time. In a recent experiment, some students at East Carolina University dropped a 12-pound shot and a rubber ball from a 125-foot tall dormitory. When the shot hit, the other ball was 25 feet off the ground. Extrapolating these results to the Tower of Pisa, which is 180 feet tall, a heavy object would have outdistanced the light one by as much as 36 feet. On our class website, I have linked a video, Galileo's Falling Bodies Experiment. Go take a look at it. So Aristotle got away with the wrong physics for centuries, but Galileo apparently invented some false lab results to rewrite the physics book for us today. To support argument number 2, free fall is uniform acceleration, Galileo could not have measured velocities to see if they were uniformly increased. Remember what uniform acceleration looks like. So here we have time in seconds, velocity meters per second. Let's say time of 0, 1, 2, 3, and 4. So if time 0, the velocity is 0, our starting point, and after 1 second, the velocity is 6 meters per second, what's the velocity in the second when we measure it here? Well, here it increased by 6. Here it should increase by another 6. The acceleration would be 6 meters per second squared. After 3 seconds, its velocity is 18 meters per second. And after 4 seconds, velocity should be 24 meters per second. This is uniform acceleration. It is accelerating uniformly every second. It doesn't have to be starting from rest. 0, 1, 2, 3, and 4 seconds. Let's say at time 0, we have a velocity of 40 meters per second. This thing is already in motion. At time of 1 second, we're at 36 meters per second. Acceleration equals, if you just look here, -4 meters per second squared, which means 32, 28, 24. The negative is uniform deceleration or uniform acceleration slowing down. Do you think Galileo students could have collected data like this at the Tower of Pisa? Did they measure velocity? Did they have a stopwatch? Galileo did an experiment that we will duplicate in class after a little math lesson that Galileo used to set up the experiment. Some formulas from Unit 1. Average velocity is distance over time. Acceleration is final velocity minus initial velocity divided by the time. For uniform acceleration, this one was special. We had final velocity plus initial velocity and divided it by 2. So for now, we will only consider motion starting at rest, which means that initial velocity equals 0. Putting together some formulas, we will derive a new formula. Average velocity is distance over time. Average velocity is v final divided by 2. Acceleration equals final velocity divided by t divided by time. So we are ignoring vi here because it's 0. Ignoring vi here because it's 0. Let's rewrite this one so that vf equals acceleration times the time. So we'll put all of these together. And so we have velocity average is distance over time. And on this other side, final velocity is AT divided by 2 makes it average velocity. So we have this average velocity on this side. We have this average velocity on this side. And this final velocity. All this to be said, divide this over, cross multiply. So 2d equals AT squared. Solving for distance gives us distance equals 1/2 times the acceleration times the time squared. So you can rearrange formulas if you know how to, if you want to. If not, this is your takeaway. Distance equals 1/2 AT squared when there's uniform acceleration with an initial velocity of 0. Another useful formula, if you solve it for A, acceleration equals twice the distance divided by the time squared. So those are your 2 important formulas for now. So if acceleration is uniform, then A is constant, which means that twice the distance divided by the square of the time is constant.